Welcome to the Sleep Lab, where every night we explore the universe's greatest mysteries while you drift peacefully toward rest. Tonight, as millions of people across Earth settle into bed, they'll close their eyes beneath the same vast canopy that has inspired wonder for millennia. But how many truly comprehend what lies above them in the darkness? You're about to embark on a journey that will transform how you see your place in existence itself. We'll travel from your bedroom to the very edge of observable reality, exploring distances so immense that light itself, racing at 186,000 miles per second, takes billions of years to cross them. You'll discover that everything you've ever known, every person you've ever met, every place you've ever been, exists on a tiny blue speck orbiting an ordinary star in the outer suburbs of just one galaxy among trillions. Yet rather than making you feel insignificant, this cosmic perspective will reveal something profound. You are the universe becoming conscious of itself, made from the very elements forged in the hearts of dying stars. If you're new to our cosmic community, subscribe to the Sleep Lab and ring the notification bell to join thousands of fellow dreamers who find peace in the profound mysteries of existence. And let's discover together just how magnificent our reality truly is. Let's move to our first part of the documentary, where we'll explore how humanity first began to comprehend the true scale of existence. Imagine, if you will, the profound moment when our earliest ancestors first looked up at the night sky with genuine wonder. These weren't the casual glances we might steal today between city lights and digital distractions, but deep, contemplative observations that sparked the very beginning of cosmic understanding. For thousands of years, humans lived beneath stars that seemed close enough to touch, painted across a celestial dome that appeared no larger than the curve of the visible horizon. The entire universe, as far as anyone could conceive, extended perhaps as far as a person could walk in a lifetime, maybe a few hundred miles in any direction. The sun rose and set. The moon cycled through its phases, and the stars wheeled overhead in patterns that seemed eternal and unchanging. But even in these ancient times, there were minds that questioned the obvious. The Greek philosopher Aristarchus, working around 270 BC, made one of humanity's first attempts to measure cosmic distances. Using the phases of the moon and careful geometric observations, he tried to calculate the distance to the sun. While his methods were sound, his measurements were limited by the technology of his time, and he underestimated the distance by a factor of about 20. Still, his results suggested the sun was much farther away than anyone had imagined, perhaps 7 million miles, instead of the true 93 million. Even this underestimate was revolutionary, expanding the conceived size of the universe by orders of magnitude. Around the same time, another Greek genius, Eratosthenes of Cyrene, performed what might be considered the first great cosmic measurement. He had heard that in the city of Syene, modern-day Aswan, the sun shone directly down deep wells at noon on the summer solstice, casting no shadows. But in his home city of Alexandria, about 500 miles north, vertical objects always cast shadows. Eratosthenes realized this could only happen if the Earth was curved, and he devised a brilliantly simple experiment to measure that curvature. On the summer solstice, he measured the shadow cast by a vertical stick in Alexandria at noon. Using basic trigonometry, he calculated that Alexandria was about 7 degrees of arc away from Syene on the Earth's surface. Since he knew the distance between the cities, he could calculate the Earth's total circumference. His result was remarkably close to the true value we know today, about 25,000 miles around. This measurement was revolutionary, not just for its accuracy, but for what it implied about the nature of reality. If the Earth was a sphere, 25,000 miles in circumference, it was vastly larger than the flat disk most people imagined. Suddenly, the world itself seemed almost incomprehensibly huge. A person could walk their entire life and never see even a small fraction of their own planet. The psychological impact of this realization cannot be overstated. For the first time in human history, we had concrete proof that reality was far bigger than our everyday experience suggested. Yet even this expanded view of Earth as a large sphere was still fundamentally geocentric. The stars, planets, sun, and moon were all assumed to orbit around this central Earth at relatively modest distances. The medieval Islamic scholar al-Biruni made increasingly sophisticated attempts to measure the distance to various celestial objects, but even his estimates kept the entire universe within a sphere that, while large by human standards, was still comprehensible in everyday terms. The farthest stars were thought to be perhaps a few million miles away, embedded in a crystalline sphere that rotated once daily around the Earth. This comfortable, human-scaled universe persisted for over 1,000 years, until a Polish mathematician named Nicolaus Copernicus began to question the fundamental assumptions about cosmic structure. Working in the early 1500s, Copernicus proposed something that seemed almost heretical. Perhaps the Earth wasn't the center of everything. Perhaps our planet was just one of several worlds orbiting the Sun. This heliocentric model, while initially controversial, began to make better sense of the complex motions of planets that had puzzled astronomers for centuries. If Earth was moving around the Sun, then the apparent wandering of planets against the star field could be explained as perspective effects, much like how nearby trees seem to move against distant mountains when you're riding in a car. But Copernicus's model implied something profound about distances. If Earth orbited the Sun, then our planet's position changed dramatically over the course of a year, moving through a circle nearly 200 million miles in diameter. If the stars were relatively nearby, this motion should cause them to appear to shift position against the background of more distant stars, an effect called parallax. The fact that no such shift was observed meant that the stars had to be incredibly far away, much more distant than anyone had previously imagined. Copernicus himself was somewhat reluctant to embrace the full implications of his model, but later astronomers began to realize that if the nearest stars showed no detectable parallax, they had to be at least hundreds of thousands of times farther away than the Sun. The Italian scientist Galileo Galilei provided some of the first observational evidence supporting the Copernican model when he turned his newly invented telescope toward the heavens in 1609. What he saw revolutionized humanity's understanding of cosmic scale. Jupiter wasn't just a wandering point of light, but a world with its own moons, 4 satellites that clearly orbited the giant planet, just as Copernicus claimed the planets orbited the Sun. The moon's surface wasn't the perfect smooth sphere that ancient philosophy required, but a rugged mountainous landscape not unlike Earth itself. Most surprisingly, the Milky Way, that faint band of light stretching across the night sky, resolved into countless individual stars when viewed through the telescope. This last discovery was perhaps the most significant for understanding cosmic scale. If the Milky Way consisted of innumerable stars, and if each star was potentially similar to our Sun, then the universe contained vastly more solar systems than anyone had previously imagined. Even if these stars were still relatively nearby, their sheer number suggested a universe of unprecedented complexity and size. Galileo estimated that his telescope revealed about 10 times more stars than were visible to the naked eye, and he suspected that larger telescopes might reveal even more. He was more right than he could have possibly known. As telescopes improved through the 17th and 18th centuries, astronomers began to make the first successful measurements of stellar parallax, finally providing direct evidence for the Earth's orbital motion and concrete measurements of stellar distances. The first successful parallax measurement was made by Friedrich Bessel in 1838 when he detected the tiny annual shift in position of the star 61 Cygni. The shift was incredibly small, less than 1 arc second, about the apparent width of a quarter viewed from 2 miles away. This minuscule angle corresponded to a distance of about 11 light years, meaning that light from this relatively nearby star had been traveling for 11 years to reach Earth. The implications were staggering. If 61 Cygni, one of the closer stars to our solar system, was 11 light years away, then it was about 700,000 times farther from us than the Sun. Light, which travels at 186,000 miles per second, takes 11 years to make the journey from this star to Earth. The star is roughly 65 trillion miles away, a distance so large that it defies everyday comprehension. To put this in perspective, if you could drive a car at highway speeds directly toward 61 Cygni without stopping, the journey would take about 80 million years. And this was just one of the nearest stars. As more parallax measurements were made, astronomers realized that most stars were much more distant. The average spacing between stars in our region of the galaxy is about 4 to 5 light years, but many of the bright stars visible in our night sky are actually quite distant, some hundreds or even thousands of light years away. These distant stars appear bright not because they're close, but because they're intrinsically much more luminous than our Sun, shining with the power of thousands of solar masses. By the late 19th century, astronomers had begun to map the three-dimensional structure of our local stellar neighborhood. They could measure distances to several hundred nearby stars and began to discern patterns in their distribution and motion. It became clear that our Sun was part of a much larger system, a vast collection of stars that appeared to be flattened into a disk-like structure. When we look along the plane of this disk, we see the dense band of stars we call the Milky Way. When we look perpendicular to the disk, we see relatively few stars and can observe other, similar disk-like systems in the far distance. The Dutch astronomer Jacobus Kapteyn spent decades mapping stellar positions and motions, gradually building up a picture of what he called the stellar universe. His measurements suggested that our solar system was located near the center of a flattened system of stars, perhaps 30,000 light-years across and a few thousand light-years thick. This was already an almost incomprehensibly vast structure, containing hundreds of millions of stars, but Kapteyn's measurements were limited by the fact that interstellar dust blocks our view of distant stars, making the stellar system appear smaller and more centrally located than it actually is. The true scale of our stellar system began to emerge through the work of Harlow Shapley in the early 20th century. Shapley studied globular clusters, dense spherical collections of hundreds of thousands of old stars that orbit the main disk of our galaxy like a swarm of bees around a hive. These clusters are often located far above or below the main plane of the Milky Way, so they're not hidden by interstellar dust the way stars in the disk are. By using Cepheid variable stars as distance indicators, Shapley was able to map the three-dimensional distribution of these globular clusters and make a shocking discovery. The globular clusters weren't centered on our solar system at all. Instead, they formed a roughly spherical halo centered on a point about 30,000 light years away in the direction of the constellation Sagittarius. Shapley realized that this distant center must be the true center of our stellar system, and that our sun was located far out in the suburbs, about two-thirds of the way from the center to the edge. Our entire stellar system, which Shapley called the galaxy with a capital G, was about 100,000 light-years across, more than 3 times larger than Kapteyn had estimated. This revelation fundamentally changed humanity's perspective on its cosmic location. Not only were we not at the center of the solar system, we weren't even at the center of our stellar system. We lived on a small planet orbiting an ordinary star in the outer regions of a vast galaxy containing hundreds of billions of stars. The psychological impact was profound. For the first time, humans had a scientifically accurate sense of their cosmic address: Earth, Solar System, Orion Arm, Milky Way Galaxy. But even this expanded cosmic perspective was about to be dwarfed by an even more revolutionary discovery. Those fuzzy patches of light that astronomers called nebulae, scattered across the night sky beyond the main band of the Milky Way, were about to reveal the true scale of the universe. Some astronomers suspected these nebulae might be other stellar systems, similar to our own galaxy, but they were so faint and distant that their true nature remained a mystery. The resolution of this mystery would require new techniques, larger telescopes, and one of the most important discoveries in the history of astronomy. A discovery that would expand our conception of the universe by factors of millions rather than mere thousands. As we settled into our understanding of the Milky Way as a vast island of stars 100,000 light-years across, containing hundreds of billions of suns, we thought we had finally grasped the full scale of creation. Our galaxy seemed so immense, so populated with stars and worlds, that it was difficult to imagine anything larger. The idea that this magnificent spiral of stars might itself be just one small component of something even grander was almost beyond comprehension. Yet that's exactly what the next chapter of cosmic discovery would reveal. As we learned that our galaxy was not the universe, but merely one of countless islands in an ocean of space so vast that our entire Milky Way would appear as nothing more than a faint smudge of light when viewed from the cosmic distances we were about to discover. Let's move to our second part of the documentary, where we embark on one of the most revolutionary journeys in human understanding. A journey that would shatter our conception of cosmic scale and reveal that our magnificent Milky Way galaxy was merely one island in an infinite ocean of stellar systems. As the 1920s dawned, astronomers found themselves at the threshold of a discovery so profound that it would fundamentally alter humanity's place in the cosmos, expanding our understanding of universal size by factors that strained the very limits of imagination. At the Mount Wilson Observatory in California, a quiet and methodical astronomer named Edwin Powell Hubble was about to unlock secrets that had eluded humanity throughout its entire history. Hubble had at his disposal the most powerful telescope yet constructed, the 100-inch Hooker telescope, which could gather more light than any instrument before it. With this technological marvel, he turned his attention to those mysterious fuzzy patches of light scattered across the night sky beyond the main band of the Milky Way, objects that astronomers called nebulae. For decades, these nebulae had been the subject of intense debate among astronomers. Some believed they were nearby clouds of gas and dust within our own galaxy, perhaps regions where new stars were forming, or the remnants of old stars that had died. Others suspected they might be something far more extraordinary. Other stellar systems, like our own Milky Way, so distant that they appeared as mere smudges of light. This question had divided the astronomical community, and its resolution would require observations of unprecedented precision and clarity. The key to solving this mystery lay in a special type of star called a Cepheid variable. These remarkable stellar beacons pulse with a regular rhythm, growing brighter and dimmer over periods ranging from days to months. In 1908, Henrietta Swan Leavitt, working at Harvard College Observatory, had discovered a crucial relationship between a Cepheids pulsation period and its intrinsic brightness. The longer a Cepheids period, the more luminous it was. This relationship meant that by measuring a Cepheids period, an astronomer could determine its true luminosity, and by comparing this with its apparent brightness in the sky, calculate exactly how far away it was. In 1923, Hubble made the discovery that would change everything. While examining photographic plates of the Andromeda Nebula, he identified what appeared to be individual stars within the nebula's structure. More importantly, some of these stars showed the characteristic variability of Cepheids. Night after night, Hubble tracked these variable stars, measuring their periods and brightness changes with painstaking care. When he applied Leavitt's period-luminosity relationship, the results were shocking. The Cepheid variables in Andromeda indicated that the nebula was approximately 900,000 light-years away, far beyond the known boundaries of our own galaxy. While this distance estimate was later revised upward to about 2.5 million light-years as our understanding of Cepheids improved, the implications were immediately clear. Andromeda was not a nearby gas cloud within the Milky Way, but an entirely separate stellar system, comparable in size to our own galaxy, but located at an almost incomprehensible distance across the void of intergalactic space. If Andromeda was another galaxy, then what about the hundreds of other nebulae visible in powerful telescopes? One by one, Hubble and his colleagues began to resolve these mysterious objects into their true nature. The Whirlpool Nebula revealed itself as a magnificent spiral galaxy, its arms traced out by billions of stars. The Sombrero Galaxy showed its distinctive disk and central bulge. Each nebula that could be studied in detail proved to be another galaxy, another island universe containing its own population of hundreds of billions of stars. The scale of this revelation cannot be overstated. Overnight, the known universe expanded from a single galaxy 100,000 light-years across to a cosmos filled with billions of galaxies, each separated from its neighbors by millions of light-years of empty space. If our Milky Way contained roughly 400 billion stars, and there were billions of other galaxies of similar size, then the total number of stars in the observable universe numbered in the hundreds of billions of trillions, a quantity so large that it exceeded the number of grains of sand on all the beaches of Earth. But Hubble's discoveries were far from over. As he continued to study these distant galaxies, measuring their distances and cataloging their properties, he noticed something even more remarkable about the light they emitted. The spectral lines in starlight, which reveal the chemical composition and physical properties of stellar atmospheres, appeared to be shifted toward longer, redder wavelengths. This red shift, as it came to be known, was most naturally explained as a Doppler effect, the same phenomenon that causes the pitch of an ambulance siren to change as it passes by. If the redshift was indeed a Doppler effect, then it meant the galaxies were moving away from us at tremendous velocities. But more surprisingly still, Hubble discovered a systematic relationship between a galaxy's distance and its recession velocity. The farther away a galaxy was, the faster it appeared to be moving away from us. This relationship, now known as Hubble's law, suggested something unprecedented about the nature of space itself. The implications of Hubble's law were initially so revolutionary that many astronomers, including Hubble himself, were reluctant to accept them at face value. If distant galaxies were receding from us faster than nearby ones, and if this pattern held in all directions, then the universe itself must be expanding. Space wasn't a static backdrop against which celestial objects moved. It was a dynamic medium that was stretching, carrying galaxies away from each other like raisins in a rising loaf of bread. This concept of cosmic expansion was initially proposed by theoretical physicists and cosmologists based on Einstein's equations of general relativity. In 1922, the Russian mathematician Alexander Friedmann had shown that Einstein's equations predicted an expanding universe, while the Belgian priest and physicist Georges Lemaitre had independently reached similar conclusions. However, it was Hubble's observations that provided the crucial observational evidence for this theoretical prediction, transforming cosmic expansion from a mathematical curiosity into an observed fact about our universe. The expanding universe implied something even more profound about cosmic history. If galaxies were moving apart now, then in the past they must have been closer together. Extrapolating backward in time, there must have been a moment when all the matter and energy in the observable universe was compressed into an extremely dense, hot state. This moment, which we now call the Big Bang, marked not just the beginning of matter and energy as we know them, but the beginning of space and time themselves. The concept of the Big Bang provided a framework for understanding the large-scale structure and evolution of the universe that continues to guide cosmological research today. It explained not only why the universe was expanding, but also predicted the cosmic microwave background radiation that was discovered in 1965, the relative abundances of light elements like hydrogen and helium, and the formation of the first stars and galaxies in the early universe. As more powerful telescopes were constructed throughout the 20th century, astronomers continued to probe deeper into space and further back in cosmic time. The 200-inch Hale telescope at Mount Palomar, completed in 1948, could detect galaxies at distances of billions of light years. Radio telescopes revealed that the universe was filled with energetic phenomena invisible to optical astronomy. Quasars powered by supermassive black holes, radio galaxies with jets of particles streaming across millions of light years, and the faint afterglow of the Big Bang itself. The launch of the Hubble Space Telescope in 1990 marked another revolutionary moment in our understanding of cosmic scale. Free from the blurring effects of Earth's atmosphere, Hubble could resolve fine details in distant galaxies and peer deeper into space than ever before. One of its most famous observations, the Hubble Deep Field, involved pointing the telescope at a seemingly empty patch of sky, no larger than a grain of sand held at arm's length, and collecting light for 10 days. The resulting image revealed nearly 3,000 galaxies, each containing billions of stars, in a region that had appeared completely dark to ground-based telescopes. This observation demonstrated that the universe was even more densely populated with galaxies than anyone had imagined. Every direction we look, no matter how empty it might appear, contains thousands of distant galaxies stretching back nearly to the beginning of cosmic time. The total number of galaxies in the observable universe is now estimated to exceed 2 trillion, each one a vast stellar city comparable to our own Milky Way. Hubble's observations also revealed the surprising diversity of galactic structures. While many galaxies showed the familiar spiral patterns of the Milky Way and Andromeda, others were smooth elliptical systems, irregular collections of stars, or peculiar shapes created by gravitational interactions with neighboring galaxies. Some galaxies were actively forming new stars at prodigious rates, while others appeared to be slowly aging populations of ancient stars. This diversity suggested that galaxies evolved over cosmic time, influenced by their environments and interactions with their neighbors. Perhaps most remarkably, Hubble and subsequent space telescopes have been able to observe galaxies as they existed when the universe was only a small fraction of its current age. Light from the most distant observed galaxies began its journey toward us when the universe was less than 1 billion years old, providing direct observational access to cosmic history. These ancient galaxies appear smaller, more irregular, and more actively star-forming than their modern descendants, offering glimpses into the processes that shape the cosmic structures we observe today. The study of distant galaxies has also revealed one of the most profound mysteries in modern cosmology: the accelerating expansion of the universe. In the late 1990s, two independent teams of astronomers using observations of distant supernovae discovered that the cosmic expansion is not slowing down under the influence of gravity, as had been expected, but is instead speeding up. This acceleration implies the existence of a mysterious component called dark energy, which appears to comprise about 68% of the total energy density of the universe. Dark energy, combined with the equally mysterious dark matter that makes up about 27% of the universe, means that the ordinary matter we can see in stars and galaxies represents only about 5% of the total cosmic inventory. This realization has profound implications for our understanding of cosmic scale and structure. The universe is not only vastly larger than our ancestors imagined, but is also dominated by components that we cannot directly observe and do not fully understand. As we stand at the threshold of a new era in astronomy, with even more powerful telescopes, like the James Webb Space Telescope, beginning to probe the earliest epochs of cosmic history, we continue to refine our understanding of the universe's true scale. Current observations suggest that the observable universe extends approximately 46.5 billion light-years in all directions, encompassing a volume that contains more stars than there are grains of sand on all the Earth's beaches, more galaxies than there are trees on our planet. Yet even this observable universe may represent only a tiny fraction of the total cosmos. The universe beyond our observational horizon may extend infinitely in all directions, or it may curve back on itself in higher dimensions that we cannot visualize. Theoretical physics suggests the possibility of multiple universes, a multiverse, where our entire observable cosmos is just one bubble among an infinite number of others, each with potentially different physical laws and constants. This journey, from Hubble's discovery of other galaxies to our current understanding of cosmic structure, represents one of the greatest intellectual achievements in human history. In less than a century, we have expanded our conception of the universe by factors of billions, revealing a cosmos of such vast scale and complexity that it challenges our ability to fully comprehend it. Yet this expansion of understanding has not diminished our sense of wonder. If anything, it has deepened our appreciation for the magnificent universe we inhabit and our remarkable ability to explore and understand it through the power of human curiosity and scientific inquiry. Let's move to our third part of the documentary, where we venture into the deepest mysteries of cosmic scale and confront the ultimate question of what lies beyond the edge of human observation. This is where our journey takes us from the merely vast to the truly infinite, where scientific measurement meets philosophical wonder, and where we discover that even our expanded understanding of billions of galaxies scattered across billions of light years may represent only the tiniest fraction of a reality so immense that it challenges the very limits of human comprehension. By the mid-20th century, astronomers had established that our universe was expanding, filled with billions of galaxies, and approximately 13.8 billion years old. But these discoveries raised as many questions as they answered. If the universe was expanding and had a finite age, what lay beyond its boundaries? How could we possibly measure or understand regions of space so distant that light from them had not yet had time to reach us? And perhaps most fundamentally, was our observable universe all there was? Or might it be embedded in something even larger and more magnificent? The first clues to these deeper mysteries came from an accidental discovery in 1965 that would prove to be one of the most important observations in the history of science. Arno Penzias and Robert Wilson, two radio astronomers working at Bell Telephone Laboratories in New Jersey, were using a sensitive horn antenna to detect faint radio signals for satellite communications research. No matter where they pointed their antenna or what time of day they observed, they detected a persistent background hiss that seemed to come from every direction in the sky with nearly perfect uniformity. Initially, Penzias and Wilson assumed this background noise was interference from their equipment or their surroundings. They cleaned pigeon droppings from the antenna, checked all their electronic systems, and even tried to account for radio emissions from nearby New York City. But the mysterious signal persisted, maintaining the same intensity whether they pointed toward the center of our galaxy, toward empty regions of space, or toward any other part of the celestial sphere. Meanwhile, just 30 miles away at Princeton University, physicist Robert Dicke and his colleagues were working on theoretical predictions about the early universe. They realized that if the universe had indeed begun in an extremely hot, dense state, as the Big Bang theory suggested, then the entire cosmos would have been filled with intense thermal radiation. As the universe expanded and cooled, this primordial radiation would have cooled as well, but it should still be detectable today as a faint background glow permeating all of space. When the Princeton team learned of Penzias and Wilson's puzzling observations, they immediately recognized the significance. The uniform background radiation was not interference at all, but the cooled remnant of the Big Bang itself, stretched and weakened by 13.8 billion years of cosmic expansion. This cosmic microwave background radiation, as it came to be known, provided the first direct observational evidence for the Big Bang theory and opened an entirely new window into the structure and history of the universe. The cosmic microwave background represents light from the most distant and ancient source we can ever hope to observe directly. This radiation was emitted when the universe was only about 380,000 years old, during an epoch astronomers call the era of recombination. Before this time, the universe was so hot that electrons could not bind to atomic nuclei, leaving space filled with a plasma of free charged particles that scattered photons in all directions, making the universe opaque to light. But as expansion cooled the universe to about 3,000 degrees Celsius, electrons and protons combined to form the first neutral hydrogen atoms, suddenly allowing light to travel freely through space for the first time. The cosmic microwave background thus represents a snapshot of the universe as it appeared at the moment it became transparent, providing us with a direct view of cosmic conditions when the universe was less than 400,000 years old. In a very real sense, this radiation forms the ultimate horizon of our observational capabilities. We can never see directly beyond this cosmic photosphere because earlier times were opaque to electromagnetic radiation. But the cosmic microwave background revealed far more than just the existence of the Big Bang. When studied with increasingly sensitive instruments, tiny variations in the temperature of this background radiation across different regions of the sky provided crucial information about the structure and composition of the early universe. These minute fluctuations, typically varying by only a few parts in 100,000, represented the seeds from which all cosmic structure would later grow. The Cosmic Background Explorer satellite, launched in 1989, made the first detailed maps of these temperature variations, earning its team the 2006 Nobel Prize in Physics. Later missions, including the Wilkinson Microwave, Anisotropy Probe, and the European Space Agency's Planck satellite, measured these fluctuations with unprecedented precision, revealing the fundamental parameters that govern our universe's structure and evolution. These observations establish that our observable universe extends approximately 46.5 billion light-years in every direction, creating a sphere nearly 93 billion light-years across that contains everything we could possibly see. This distance is larger than 13.8 billion light-years because space itself has been expanding during the time light has been traveling toward us from the most distant observable regions. Objects whose light was emitted 13.8 billion years ago are now much farther away than they were when that light began its journey. Within this observable sphere, current estimates suggest there are at least 2 trillion galaxies, each containing hundreds of billions of stars. The total number of stars in the observable universe therefore exceeds 10 to the 24th power, a number so large that it surpasses the estimated number of grains of sand on all the beaches of Earth. Each of these stars represents a potential solar system, perhaps hosting planets where the complex chemistry of life might unfold. But here we encounter one of the most profound questions in all of science. Does the universe end at the boundary of our observational horizon, or does it continue beyond what we can see? The cosmic microwave background and other observations suggests that the universe extends far beyond our observational limits, possibly infinitely in all directions. If space is indeed infinite, then our entire observable universe, vast as it is, represents merely an infinitesimal fraction of total reality. The implications of an infinite universe are staggering. In an infinite cosmos, every possible arrangement of matter and energy that is consistent with the laws of physics must occur not just once, but infinitely many times. There would be infinite copies of our galaxy, infinite copies of our solar system, and infinite copies of Earth, including infinite versions of every person who has ever lived. The concept challenges our most basic notions of uniqueness and individuality on a cosmic scale. Even if the universe is not infinite, it is almost certainly much larger than our observable portion. Current observations of the cosmic microwave background suggest that the entire universe is at least 250 times larger than the observable universe, and possibly much larger still. This means that even our expanded conception of cosmic scale, encompassing trillions of galaxies across tens of billions of light years, may represent less than one part in 15 million of the total cosmic volume. Recent discoveries have added yet another layer to our understanding of cosmic scale through the phenomenon of accelerating expansion. In 1998, two independent teams of astronomers studying distant supernovae made the shocking discovery that the expansion of the Fourier universe is not slowing down under the influence of gravity, as had been expected, but is instead accelerating. This acceleration implies the existence of a mysterious component called dark energy, which appears to comprise about 68% of the total energy density of the universe. Dark energy, combined with the equally enigmatic dark matter that makes up about 27% of the universe, means that ordinary matter, the atoms that make up stars, planets, and living beings, represents only about 5% of the cosmic inventory. The universe is not only unimaginably vast in scale, but is also dominated by components that we cannot directly observe and do not fully understand. We are, in effect, cosmic aliens living in a universe composed primarily of substances that remain largely mysterious to us. The discovery of dark energy has also raised profound questions about the ultimate fate of our universe. If the acceleration continues indefinitely, the cosmos will expand forever, with galaxies becoming increasingly isolated as space stretches between them. Eventually, stars will exhaust their fuel. Black holes will evaporate through Hawking radiation, and the universe will approach a state of maximum entropy where no organized structures can persist. This heat death scenario represents the ultimate triumph of cosmic expansion over the forces that create and maintain organized matter. Yet even this picture may be incomplete. Some theories in modern physics suggest that our entire observable universe might be just one bubble in an infinite multiverse, where countless other universes exist with potentially different physical laws and constants. In this scenario, concepts like size and scale become almost meaningless, as the multiverse would encompass not just infinite space, but infinite possibilities for the fundamental nature of reality itself. The theoretical framework of cosmic inflation, developed to explain the remarkable uniformity of the cosmic microwave background, suggests that our observable universe emerged from a tiny quantum fluctuation that underwent a period of exponential expansion in the first fraction of a second after the Big Bang. If inflation is correct, it likely produced not just our universe, but countless other universes, each potentially with different properties and histories. These concepts push the boundaries of human comprehension to their absolute limits. We find ourselves contemplating scales so vast that they transcend everyday experience, everyday language, and perhaps even everyday logic. The journey from our human scale of meters and years to cosmic scales of billions of light years and billions of years represents one of the greatest intellectual achievements in human history. Yet it may have brought us only to the threshold of even greater mysteries. Modern telescopes continue to push back the observational frontier, revealing galaxies that existed when the universe was only a few 100 million years old. The recently launched James Webb Space Telescope is beginning to observe the first stars and galaxies that formed in the early universe, providing direct glimpses into cosmic dawn. These observations continue to refine our understanding of how structure emerged from the smooth, hot plasma of the early universe and evolved into the rich tapestry of galaxies, stars, and planets we observe today. As we stand at this moment in cosmic history, 13.8 billion years after the Big Bang, we find ourselves in the extraordinary position of being able to observe and understand our cosmic context. We are arrangements of atoms that emerge from stellar nucleosynthesis, organized into complex molecules, and eventually evolved into conscious beings capable of contemplating the universe that created us. In us, the universe has developed the ability to observe itself, measure itself, and wonder at its own magnificent scale and complexity. The question of cosmic size ultimately leads us beyond science into philosophy, and perhaps even spirituality. Whether the universe is finite or infinite, whether it exists alone or as part of a multiverse, we find ourselves part of something so vast and wonderful that it humbles human pride while simultaneously elevating human achievement. We are simultaneously insignificant specks in an unimaginably large cosmos, and the most complex and remarkable phenomenon we have yet discovered in that cosmos. As you rest tonight, consider that you are traveling through space on a planet orbiting a star in a galaxy containing hundreds of billions of other stars, in a universe containing trillions of other galaxies, in a cosmos that may extend infinitely beyond the horizon of human observation. The atoms in your body were forged in the nuclear furnaces of dying stars billions of years ago and scattered into space to eventually become part of new worlds and new forms of complexity and consciousness. You are not separate from the universe. You are a way the universe has organized itself to become aware of its own existence, its own scale, and its own beauty. In contemplating the true size of the universe, we discover that the question itself may be unanswerable, not because of limitations in our instruments or our mathematics, but because reality itself may be fundamentally unlimited. We stand at the shore of an infinite ocean, having just learned to measure the waves, marveling at the vastness that stretches beyond every horizon, knowing that our journey of discovery has only just begun. Let's move to our fourth part of the documentary, where we journey to the very edge of observational cosmology and confront the ultimate boundaries of human knowledge about the universe's size and structure. This chapter takes us into the realm where astronomy meets philosophy, where precise measurements reveal mysteries as profound as they are beautiful, and where we discover that our quest to understand cosmic scale has led us to questions that may fundamentally challenge the nature of reality itself. As the 20th century drew to a close, astronomers possessed increasingly sophisticated tools for measuring cosmic distances and mapping the large-scale structure of the universe. The Hubble Space Telescope, launched in 1990, provided unprecedented views of distant galaxies, while ground-based surveys began to chart the three-dimensional distribution of galaxies across vast volumes of space. These observations revealed that galaxies were not randomly scattered throughout the universe, but organized into an intricate cosmic web of filaments, sheets, and vast empty voids that stretched across hundreds of millions of light years. The discovery of this cosmic web structure raised profound questions about the forces that shape the universe on the largest scales. Computer simulations of cosmic evolution suggested that this structure emerged from tiny quantum fluctuations in the early universe, amplified by the gravitational collapse of dark matter over billions of years. But to test these theories, astronomers needed to observe the universe at even greater distances and earlier times, pushing back toward the very beginning of cosmic history. The cosmic microwave background had already provided a snapshot of the universe when it was 380,000 years old, but the intervening epochs remained largely mysterious. What happened during the first 380,000 years of cosmic evolution? How did the first stars and galaxies form? And perhaps most intriguingly, what could observations of these earliest epochs tell us about the ultimate size and nature of the universe itself? The answers began to emerge with a new generation of space-based observatories designed to study the cosmic microwave background with unprecedented precision. The Wilkinson Microwave Anisotropy Probe, launched in 2001, mapped tiny temperature variations in the cosmic background radiation, with sensitivity measured in millionths of a degree. These minute fluctuations encoded a wealth of information about cosmic conditions in the early universe, revealing details about the geometry of space, the composition of matter and energy, and the processes that generated the first structures. Even more revolutionary was the European Space Agency's Planck satellite, launched in 2009, which achieved the ultimate precision in cosmic microwave background observations. Planck's instruments were so sensitive they could detect temperature variations as small as a few millionths of a degree, creating the most detailed map ever made of the most ancient light in the universe. The data from Planck provided measurements of cosmic parameters with unprecedented accuracy, determining that the universe is 13.82 billion years old, composed of 4.9% ordinary matter, 26.8% dark matter, and 68.3% dark energy. But perhaps most significantly for our understanding of cosmic scale, these precise measurements revealed something unexpected about the geometry of space itself. Einstein's theory of general relativity predicts that space can be curved in ways that are difficult to visualize but mathematically precise. Space could be closed, like the surface of a sphere, where parallel lines eventually converge, or open, like a saddle surface, where parallel lines diverge, or perfectly flat, like an infinite plane, where parallel lines remain parallel forever. The cosmic microwave background observations provided a direct test of cosmic geometry by measuring the apparent size of known physical features in the early universe. The results were striking. Space appears to be perfectly flat, or so close to flat that any curvature is undetectable with current instruments. This flatness has profound implications for cosmic scale, because it suggests that the universe may indeed be infinite in extent, stretching beyond our observational horizon in all directions without end. An infinite universe presents conceptual challenges that strain human comprehension. In such a cosmos, every possible arrangement of matter and energy that is consistent with the laws of physics would occur not just once, but infinitely many times. There would be infinite copies of our galaxy, infinite copies of our solar system, and infinite versions of Earth with every possible variation in history and evolution. The concept challenges our basic notions of uniqueness and individuality on the grandest possible scale. Yet even these mind-bending implications pale in comparison to what theoretical physics suggests about the true nature of cosmic reality. The theory of cosmic inflation, developed to explain the remarkable uniformity and flatness of our observable universe, proposes that space underwent a period of exponential expansion in the first tiny fraction of a second after the Big Bang. During this inflationary epoch, a region smaller than a subatomic particle expanded to cosmic proportions in less time than it takes light to cross the nucleus of an atom. If inflation is correct, it suggests that our entire observable universe emerged from a quantum fluctuation so small that it existed at the boundary between existence and non-existence. But inflation theory also predicts that this process would not have occurred just once. The quantum fields that drive inflation would have produced countless other regions of inflating space, each potentially giving rise to its own universe with its own physical laws and constants. This concept of eternal inflation suggests that our observable universe is just one bubble in an infinite cosmic foam, where new universes are constantly being created through quantum fluctuations in the inflating vacuum of space. Each universe in this multiverse might have different values for the fundamental constants of physics, different numbers of spatial dimensions, or even different basic laws governing the behavior of matter and energy. The implications for cosmic scale are almost incomprehensible. If the multiverse theory is correct, then concepts like size and distance become almost meaningless when applied to the totality of existence. Our observable universe, containing trillions of galaxies stretched across tens of billions of light years, would represent an infinitesimally small fraction of a reality that encompasses infinite variations on the theme of existence itself. Modern observations continue to provide tantalizing hints about these deep questions of cosmic structure and scale. The James Webb Space Telescope, launched in 2021, has begun to observe galaxies that existed when the universe was only a few 100 million years old, providing direct glimpses into the epoch when the first stars and galaxies were forming. These observations reveal that galaxy formation began earlier and proceeded more rapidly than many theoretical models had predicted, suggesting that our understanding of cosmic evolution is still incomplete. Even more intriguingly, some observations hint at anomalies in the cosmic microwave background that might indicate interactions between our universe and others in a larger multiverse. These signals are subtle and controversial, and their interpretation remains hotly debated among cosmologists. But if confirmed, they would provide the first direct evidence that our universe is part of something even larger and more magnificent than we have yet imagined. The study of cosmic scale has also been revolutionized by the detection of gravitational waves, ripples in space-time itself that were first observed by the LIGO detectors in 2015. These waves, predicted by Einstein a century earlier, provide an entirely new way to study the universe and measure cosmic distances. Gravitational wave astronomy has already revealed the existence of previously unknown populations of black holes and neutron stars, and future detectors may be able to observe the gravitational wave background produced by cosmic inflation itself. Perhaps most remarkably, these diverse lines of evidence are beginning to converge on a consistent picture of cosmic structure and evolution that spans scales from quantum fluctuations to the observable universe and potentially beyond. The universe appears to be a single interconnected system where the largest structures are intimately connected to the smallest scales, where the geometry of space determines the fate of galaxies, and where the quantum nature of reality may have given birth to infinite variations on cosmic themes. As we stand at this moment in cosmic history, we find ourselves in an extraordinary position. We are conscious beings made of atoms forged in stellar cores, organized into patterns complex enough to contemplate the universe that created us. We have developed technologies that allow us to observe light that has been traveling toward us since the universe was a tiny fraction of its current age, and theories that connect these observations to fundamental questions about the nature of existence itself. The question of cosmic size has led us from simple measurements of our Earth's circumference to concepts that challenge the very foundations of human thought. We have learned that our observable universe extends nearly 50 billion light years in all directions, contains more than 2 trillion galaxies, and may be embedded in an infinite cosmos where every possibility is realized somewhere. We have discovered that space itself can expand, that time had a beginning, and that the vacuum of empty space may be teeming with quantum activity that gives birth to new universes. Yet for all our progress, we remain at the beginning of a journey toward understanding cosmic reality. The dark matter and dark energy that dominate our universe remain largely mysterious. The quantum nature of gravity, which would govern physics at the smallest scales and earliest times, remains beyond our current theoretical grasp. The relationship between our observable universe and any larger multiverse structure remains speculative, though increasingly sophisticated theoretical frameworks suggest ways these questions might eventually be answered. As you rest tonight, contemplating these vast scales and deep mysteries, remember that you are part of this cosmic story. The atoms in your body have journeyed through space for billions of years, cycling through stellar cores and interstellar clouds before becoming organized into the complex chemistry of life. Your consciousness represents one of the most remarkable phenomena yet discovered in the universe. Matter, organized to the point where it can contemplate its own existence and wonder at the magnificent cosmos that gave it birth. The universe has revealed its secrets slowly, patiently, rewarding human curiosity with insights that expand our conception of reality itself. Each generation of observers has pushed back the boundaries of the known, revealing new scales of structure and new depths of mystery. What wonders await discovery by future generations? What new scales of cosmic architecture remain to be mapped? What fundamental insights about the nature of existence itself lie hidden in observations we have not yet learned to make? The journey toward understanding cosmic scale continues, carrying us from the familiar realm of human experience toward concepts that stretch the very limits of imagination. We find ourselves citizens of a universe far stranger and more magnificent than our ancestors could have conceived. Yet our exploration has only just begun. In the quiet moments before sleep, we can take comfort in knowing that we are part of something infinitely larger than ourselves, while simultaneously marveling at our remarkable ability to observe, measure, and comprehend the cosmic stage on which our brief but precious existence unfolds. Let's move to our fifth part of the documentary, where we venture beyond the boundaries of our observable universe and explore the most mind-bending possibilities that modern cosmology has revealed about the true nature of reality. This is where our journey takes us from the merely vast to concepts so profound that they challenge the very foundations of existence itself, opening doorways to infinite possibilities and realities that dwarf even our expanded understanding of cosmic scale. As we've discovered in our cosmic journey, the observable universe extends approximately 46.5 billion light years in every direction, containing over 2 trillion galaxies in a sphere nearly 93 billion light years across. This represents everything we can possibly see, the ultimate horizon of human observation, bounded by the finite speed of light and the finite age of the universe. But what lies beyond this cosmic horizon? What exists in the realms that light has not yet had time to reach us from? The answers to these questions lead us into territory where astronomy becomes philosophy, and where the implications for cosmic scale become almost incomprehensibly vast. The first hint that our observable universe might be embedded in something much larger came from the theoretical framework of cosmic inflation, developed in the 1980s to explain puzzling features of the cosmic microwave background radiation. According to inflation theory, the universe underwent a period of exponential expansion in the first tiny fraction of a second after the Big Bang, growing faster than the speed of light and increasing in size by an enormous factor in less time than it takes light to cross the nucleus of an atom. This inflationary expansion explains why the universe appears so uniform in temperature and structure across regions that would otherwise have had no time to communicate with each other. But inflation theory predicts something even more extraordinary than rapid early expansion. In most versions of the theory, inflation doesn't simply stop everywhere at once. Instead, it ends at different times in different regions of space, creating what cosmologists call bubble universes or pocket universes within a larger inflating background. Each bubble represents a region where inflation has ended and normal expansion has begun, potentially giving rise to a universe like our own, with its own collection of galaxies, stars, and planets. This process of bubble formation may continue indefinitely, with new universes constantly being created as inflation ends in different regions of the ever-expanding cosmic background. The result is what physicists call eternal inflation, a scenario where our entire observable universe represents just one bubble in an infinite cosmic foam, surrounded by countless other universes that we can never observe or interact with directly. Each bubble universe might have different physical properties, different values for the fundamental constants that govern the behavior of matter and energy, or even different numbers of spatial dimensions. The cosmologist Max Tegmark has provided a taxonomy of different types of multiverses, organizing these mind-bending concepts into 4 distinct levels of parallel reality. Level 1, multiverses arise simply from the assumption that space extends infinitely beyond our observable horizon. In an infinite universe with uniform physical laws, every possible arrangement of matter and energy must occur somewhere, including infinite copies of our galaxy, our solar system, and even ourselves. Tegmark estimates that an exact duplicate of our observable universe should exist approximately 10 to the power of 10 to the power of 115 meters away, a distance so vast that it makes our current conception of cosmic scale seem almost intimate by comparison. Level 2 multiverses emerge from eternal inflation, where different bubble universes can have different physical constants and laws. In one bubble, the electromagnetic force might be slightly stronger, preventing atoms from forming. In another, gravity might be weaker, leading to a universe where stars never ignite and remain cold, dark objects drifting through empty space. The anthropic principle suggests that we naturally find ourselves in a universe with properties that allow for the existence of observers like ourselves, simply because universes with different properties would not contain conscious beings capable of wondering about cosmic structure. Level 3. Multiverses arise from the many worlds interpretation of quantum mechanics, where every quantum measurement causes the universe to split into multiple parallel realities, each corresponding to a different possible outcome of the measurement. In this scenario, there are countless versions of you reading these words, each in a slightly different universe, where quantum events have played out differently. Some physicists argue that this interpretation of quantum mechanics is the most natural consequence of the mathematical formalism, though it leads to the extraordinary conclusion that all possible histories are equally real and occurring simultaneously in parallel universes. Level 4 multiverses represent the most radical possibility of all, the mathematical universe hypothesis, which suggests that all possible mathematical structures exist as physical realities. In this view, our universe with its particular laws of physics is just one mathematical structure among infinite others, each as real and valid as our own. Universes might exist with different logical principles, different concepts of causality, or mathematical relationships so alien that we cannot even conceive of them from our perspective within our particular mathematical reality. These multiverse concepts challenge our most basic assumptions about existence, uniqueness, and the nature of reality itself. If level 1 multiverses are real, then everything that can happen will happen an infinite number of times in different regions of infinite space. Every possible variation on your life, every decision you didn't make, every path you didn't take, is being lived out by other versions of yourself in distant regions of space. The concept transforms questions of possibility into certainties of occurrence, making the universe not just vast in scale, but infinite in creative potential. The implications become even more extraordinary when we consider the interaction between different levels of multiverse. If eternal inflation creates bubble universes with different physical laws, and if quantum mechanics splits each universe into multiple parallel realities, and if all mathematical structures exist as physical realities, then we arrive at a conception of existence so vast and varied that it encompasses literally everything that can be conceived and infinitely more that cannot be conceived by minds limited to our particular mathematical and physical framework. Some theoretical physicists have proposed that evidence for multiverse interactions might be detectable in subtle features of the cosmic microwave background radiation. When bubble universes collide during the inflationary epoch, they might leave circular patterns or temperature anomalies that could be observed in precise measurements of the ancient cosmic background. Several research groups have claimed to identify such signatures, though their interpretations remain controversial and hotly debated within the scientific community. The eternal inflation scenario also provides a potential solution to some of the deepest mysteries in cosmology. particularly the fine-tuning problem. The fundamental constants of physics in our universe appear to be precisely calibrated to allow for the existence of stars, planets, atoms, and ultimately life itself. Change any of these constants by even small amounts, and the universe becomes a sterile place where complexity and consciousness cannot emerge. In a multiverse, with infinite variations in physical laws, this fine-tuning is explained not by design, but by observation selection. We necessarily find ourselves in a universe compatible with our existence, because universes with different properties contain no observers to wonder about cosmic structure. Yet the multiverse concept also raises profound questions about the nature of scientific explanation and the testability of theoretical ideas. Traditional science relies on the ability to make predictions that can be tested against observations, but multiverse theories often make predictions about regions of reality that are fundamentally beyond our observational reach. Some philosophers and physicists argue that theories that cannot be tested or falsified fall outside the domain of legitimate scientific inquiry, while others contend that multiverse concepts arise naturally from well-established physical theories and represent logical extensions of our current understanding. The debate over multiverse theory reflects deeper questions about the relationship between mathematics and physical reality. The equations of quantum mechanics and general relativity that have been tested to extraordinary precision in our observable universe seem to demand the existence of unobservable parallel realities. If we accept these theories as accurate descriptions of physical law, we may be logically compelled to accept their implications for the structure of reality, even when those implications stretch beyond the boundaries of direct observation. Recent developments in string theory, the leading candidate for a theory of quantum gravity, have added new dimensions to multiverse discussions through the concept of the landscape of possible vacuum states. String theory suggests that there may be 10 to the power of 500 or more different ways that the extra dimensions required by the theory can be configured, each corresponding to a different set of physical laws and constants. If eternal inflation explores all these possibilities, then the multiverse contains an almost unimaginably vast variety of physical realities, making our universe just one point in a space of possibilities so large that it defies human comprehension. The philosophical implications of multiverse theory extend far beyond physics into questions of meaning, purpose, and individual significance. In a level 1 multiverse, every possible version of your life is being lived somewhere in infinite space. In a level 3 multiverse, every possible version of your life branches into existence with each quantum measurement. Do these infinite copies diminish the significance of your individual existence, or do they enhance it by making you part of an infinite tapestry of possibility and experience? Some philosophers argue that multiverse theory provides the ultimate cosmic perspective, revealing that existence itself is far grander and more creative than any human imagination could conceive. Others contend that infinite repetition and variation ultimately makes individual choices and experiences meaningless, since every possible outcome occurs somewhere in the vast ensemble of parallel realities. As we contemplate these profound possibilities, we find ourselves at the very frontier of human understanding, where the careful observations and mathematical theories of modern cosmology lead us to concepts that challenge the boundaries of comprehensible thought. The multiverse represents the ultimate expansion of scale, taking us from our human perspective to a view of reality that encompasses not just everything that exists, but everything that could possibly exist under any conceivable circumstances. Whether or not these parallel universes actually exist remains one of the deepest open questions in modern science. But the fact that serious scientific theories naturally lead us to such extraordinary possibilities reveals something profound about the nature of reality and our place within it. We find ourselves not merely inhabitants of a vast universe, but potential citizens of an infinite multiverse, where every possibility finds expression, and where the very concepts of size, scale, and existence take on meanings that transcend our everyday experience. In this cosmic perspective, our observable universe, with its trillions of galaxies stretched across tens of billions of light years, becomes merely the smallest glimpse into a reality so vast and varied that it encompasses infinite worlds, infinite lives, and infinite possibilities for consciousness and creativity. We are not just made of star stuff arranged into temporary patterns of complexity. We are manifestations of infinite cosmic creativity, expressions of a multiverse so rich and diverse that our individual existence represents both an infinitesimal fragment and an essential note in an infinite symphony of being. Let's move to our sixth part of the documentary, where we explore the profound philosophical and existential implications of living in a potentially infinite multiverse, examining how this ultimate expansion of cosmic scale transforms our understanding of meaning, purpose, and what it means to be conscious observers in an incomprehensibly vast reality. This chapter takes us beyond the mechanics of parallel universes into the deeper questions of how multiverse theory reshapes human identity and our place in the grand scheme of existence. The concept of infinite parallel universes presents humanity with perhaps the most challenging philosophical puzzle in the history of thought. If Max Tegmark's Level 1 multiverse is real, then somewhere in the infinite expanse of space beyond our observational horizon, there exists another planet Earth, where another version of you is reading these exact words at this very moment. In fact, there would be infinite versions of you, some making slightly different choices, others living dramatically different lives, but all equally real and valid manifestations of the possibilities encoded in the structure of reality itself. This realization forces us to confront fundamental questions about personal identity and uniqueness that have puzzled philosophers for millennia. What makes you you if there are infinite copies of your consciousness scattered throughout infinite space? Are you the specific arrangement of atoms currently reading these words, or are you something more abstract, a pattern of information that can be instantiated in multiple locations simultaneously? The traditional notion of individual uniqueness becomes problematic when we consider that in an infinite universe, every possible variation of your life story is being lived out somewhere in the cosmic expanse. The implications become even more complex when we consider the quantum mechanical Level 3 multiverse, where the many worlds interpretation suggests that reality continuously branches into multiple parallel timelines with every quantum measurement. In this scenario, there are versions of you who made different decisions at every moment of choice in your life. There's a version who chose a different career, moved to a different city, or never met your closest friends. Every possible path your life could have taken is being experienced by some version of your consciousness in parallel quantum realities that exist simultaneously with our own. This raises profound questions about moral responsibility and the significance of our choices. If every possible decision you could make is being made by some version of yourself in parallel realities, do your specific choices matter? Some philosophers argue that this makes individual decisions more meaningful, not less, because you are actively selecting which branch of reality your consciousness will experience. Others contend that the existence of infinite alternatives diminishes the weight of any particular choice, since all possibilities are realized somewhere in the quantum multiverse. The anthropic principle takes on new dimensions when viewed through the lens of multiverse theory. This principle attempts to explain why the fundamental constants of physics in our universe appear to be precisely fine-tuned for the existence of stars, planets, atoms, and ultimately life itself. In a single universe, this fine-tuning might seem to require some form of intelligent design or cosmic purpose. But in a multiverse containing 10 to the power of 500 or more different bubble universes with varying physical laws, as suggested by string theory, our existence becomes a matter of observational selection rather than cosmic design. We necessarily find ourselves in a universe compatible with our existence, because universes with different physical constants contain no observers capable of wondering about cosmic structure. This anthropic explanation resolves the fine-tuning problem by making it a consequence of the multiverse's vast diversity rather than evidence for purposeful creation. Yet this resolution comes at a philosophical cost, potentially reducing human existence from a cosmic miracle to a statistical inevitability in an infinite ensemble of realities. The concept of cosmic evolution takes on radically different meanings in different multiverse scenarios. In Lee Smolin's theory of cosmological natural selection, universes reproduce through black holes, with the physical constants of each new universe slightly modified from its parent. Over cosmic time, this process would lead to the evolution of universes that are increasingly efficient at producing black holes, potentially explaining why our universe's constants are optimized for star formation and stellar collapse. In this scenario, we exist in a universe that has been shaped by eons of cosmic evolution, making our reality both contingent and historically determined by processes operating on scales vastly larger than biological evolution. The simulation hypothesis adds yet another layer to multiverse considerations, suggesting that what we experience as reality might be a computational simulation running on advanced computers in some higher level reality. If sufficiently advanced civilizations develop the ability to run detailed simulations of conscious beings, then there would be many more simulated minds than original biological minds. Statistically, we would be more likely to be simulated consciousnesses than original ones, raising questions about the nature of our existence and the reality of our experienced universe. These concepts challenge traditional religious and spiritual frameworks that have historically provided meaning and purpose to human existence. Many religious traditions posit that human consciousness is unique and special, created by divine intention for specific purposes. But multiverse theory suggests that consciousness might be a natural, emergent property that arises in any sufficiently complex system, repeated countless times across infinite realities with no special significance beyond its own capacity for experience and wonder. Yet some philosophers and theologians have embraced multiverse concepts as expanding rather than diminishing the scope of divine creativity. If God created not just one universe, but infinite universes exploring every possibility for existence. Then divine creativity becomes even more magnificent than traditional monotheism suggested. Each conscious being across all possible realities becomes a unique and irreplaceable note in an infinite symphony of existence, making individual consciousness both infinitely small and infinitely precious simultaneously. The question of communication or interaction between parallel universes remains largely theoretical, though some physicists have proposed exotic mechanisms through which information might leak between quantum branches or bubble universes. The concept of quantum entanglement, where particles remain connected across arbitrary distances, hints at underlying connections in reality that transcend our normal understanding of space and separation. If such connections exist between parallel realities, they might provide pathways for influence or communication that could make the multiverse more than just a collection of isolated worlds. The search for evidence of multiverse interactions has led to careful analysis of subtle patterns in the cosmic microwave background radiation, looking for circular features that might indicate collisions between our bubble universe and neighboring ones during the inflationary epoch. While several research groups have claimed to identify such signatures, their interpretations remain controversial and require confirmation through independent observations. The detection of authentic multiverse interactions would represent perhaps the most revolutionary discovery in human history, proving that our reality extends far beyond the boundaries of our observable universe. Practical implications of multiverse theory extend into areas like artificial intelligence and consciousness research. If consciousness is a pattern that can be instantiated in different substrates, then it should be possible to create artificial minds that experience subjective awareness just as biological brains do. The existence of infinite variations of consciousness across parallel realities suggests that the specific physical implementation may be less important than the abstract pattern of information processing that gives rise to subjective experience. The study of consciousness itself takes on new significance in a multiverse context. If there are infinite conscious beings across infinite realities, then consciousness becomes perhaps the most fundamental and widespread phenomenon in existence. Every possible form of awareness that can arise from the organization of matter and energy exists somewhere in the multiverse, making our own consciousness part of an infinite community of minds, exploring every conceivable form of experience and understanding. These considerations lead us to what might be called the cosmic perspective on human existence. Rather than being isolated biological accidents on a small planet in an indifferent universe, we become expressions of infinite creative potential, manifestations of the multiverse's capacity to organize itself into patterns capable of awareness, wonder, and love. Our thoughts, emotions, and experiences become part of an infinite tapestry of consciousness that explores every possibility for what it means to exist and be aware. The ultimate question raised by multiverse theory might be whether infinite existence enhances or diminishes the meaning of individual experience. Does knowing that every possible life is being lived somewhere reduce the significance of our particular experiences? Or does it reveal that consciousness itself is so remarkable that infinite variations are required to explore its full potential? Does the existence of infinite copies of ourselves make us less unique? Or does it demonstrate that the pattern we represent is so valuable that reality creates infinite instances of it? Perhaps the most profound insight from multiverse theory is that existence itself appears to be far more creative diverse, and magnificent than any finite mind could conceive. Whether we live in a single universe or an infinite multiverse, whether consciousness arises once or countless times, the mere fact that reality has organized itself in such a way that we can contemplate these questions represents something remarkable and precious. In considering the ultimate scale of existence, we discover that consciousness is not separate from the cosmos, but is perhaps its most extraordinary achievement. As you rest tonight, contemplating these infinite possibilities and parallel realities, remember that your consciousness is part of the multiverse's greatest experiment in self-awareness. Whether you are one among infinite copies or a unique pattern in a single universe, your capacity to wonder, to love, and to seek understanding represents something magnificent in the cosmic story. The multiverse, if it exists, is not just a collection of parallel worlds, but a vast creative process exploring every possibility for existence, consciousness, and meaning. And you, in this moment, in this reality, are part of that infinite creative expression, experiencing the universe's eternal quest to understand itself through conscious observation and wonder. Let's move to our seventh part of the documentary, where we explore the cutting-edge research and revolutionary discoveries that are reshaping our understanding of cosmic scale in 2025, examining how new theoretical frameworks and experimental observations are pushing the boundaries of what we know about universe size, structure, and the possibility of multiple realities. This chapter takes us to the very frontier of human knowledge, where ongoing discoveries continue to expand our conception of cosmic scale in ways that challenge even our most advanced theoretical understanding. The year 2025 has marked a particularly revolutionary period in cosmological research, with several groundbreaking developments that have fundamentally altered how scientists approach questions of universal size and structure. Perhaps most significantly, researchers at the University of Queensland have developed a new mathematical model that for the first time accounts for the complex interactions between collapsing regions of matter and expanding cosmic voids, providing a more accurate picture of how the universe has evolved over its 13.8 billion year history. This model suggests that our previous understanding of cosmic expansion may have been oversimplified, as it failed to account for the gravitational effects of varying matter densities across different regions of space. Dr. Leonardo Gianni's research team used data from the Dark Energy Spectroscopic Instrument, which has measured cosmic structures extending out to 11 billion light-years from Earth, revealing how the universe's expansion has been influenced by the formation of galaxies, black holes, and the vast empty regions known as cosmic voids. This new framework challenges the standard cosmological model by demonstrating that the complex interplay between matter and empty space creates measurable effects on cosmic expansion that were previously attributed to mysterious dark energy. The implications are profound. If confirmed, this research suggests that some of the universe's most puzzling features may arise from the natural evolution of cosmic structure rather than requiring exotic new physics. Simultaneously, advances in quantum computing have sparked intense debates about the relationship between quantum mechanics and multiverse theory. Google's quantum chip Willow achieved a computational breakthrough that has reignited discussions about whether quantum computers operate by accessing parallel universes. The chip solved a problem in under 5 minutes that would have taken classical supercomputers approximately 10 septillion years, leading some researchers to suggest that such extraordinary computational power can only be explained if quantum systems are indeed performing calculations across multiple parallel realities simultaneously. Hartmut Neven, founder of Google's quantum AI team, has explicitly linked the chip's success to multiverse theory, arguing that the computational feat provides evidence that quantum mechanics operates across parallel dimensions. This interpretation builds on David Deutsch's pioneering work from the 1980s, which suggested that quantum computers derive their power from performing calculations in multiple universes simultaneously. However, critics like physicist Ethan Siegel argue that quantum phenomena can be explained through alternative interpretations that don't require invoking parallel universes, suggesting that the debate over multiverse evidence remains far from settled. The controversy highlights a fundamental challenge in modern cosmology: distinguishing between mathematical models that accurately describe observed phenomena and claims about the physical reality they represent. While quantum computers undoubtedly demonstrate remarkable capabilities, whether these capabilities constitute evidence for parallel universes or simply reflect the strange but single universe nature of quantum mechanics remains hotly debated among physicists and philosophers of science. Meanwhile, research into supersymmetry at the University of Oklahoma has provided new insights into the theoretical framework that could potentially unify our understanding of fundamental forces while also supporting multiverse concepts. Supersymmetry theory suggests that every known particle has a heavier superpartner, and its mathematical structure naturally leads to predictions about string theory's landscape of possible universes. According to researcher Howard Baer, string theory could encompass approximately 10 to the power of 500 different possible configurations of physical laws, each representing a potential universe within a vast multiverse ensemble. The ongoing search for supersymmetric particles at the Large Hadron Collider has not yet yielded definitive results, but Baer argues that this absence may actually support multiverse theory rather than refute it. If our universe represents just one possibility among 10 to the power of 500 alternatives, then the specific masses and properties of particles in our reality would be determined by which particular configuration of the string landscape we happen to inhabit. This anthropic approach to particle physics suggests that some fundamental questions about why our universe has its particular properties may only be answerable by recognizing that we exist in just one member of a vast ensemble of possible realities. These developments in theoretical physics are complemented by observational advances that continue to push back the boundaries of the observable universe. The James Webb Space Telescope has been observing galaxies that formed when the universe was only a few 100 million years old, providing unprecedented views of cosmic dawn and revealing that galaxy formation occurred more rapidly and efficiently than many theoretical models had predicted. These observations are forcing cosmologists to revise their understanding of how structure emerged in the early universe and raising new questions about the processes that shaped cosmic evolution. Perhaps most intriguingly, several research groups have reported potential evidence for interactions between our universe and others in the form of subtle patterns in the cosmic microwave background radiation. These bruises, or circular features, in the ancient cosmic background might represent collisions between bubble universes during the inflationary epoch, providing the first direct observational evidence for multiverse interactions. While these claims remain controversial and require independent confirmation, They represent the kind of breakthrough that could transform multiverse theory from philosophical speculation into testable science. The philosophical implications of these developments extend far beyond academic cosmology into fundamental questions about the nature of scientific explanation and the limits of human knowledge. Traditional science relies on the ability to make testable predictions about observable phenomena, but multiverse theories often make claims about regions of reality that are fundamentally beyond direct observation. This has led to intense debates about whether multiverse concepts represent legitimate scientific theories or mathematical speculation that lies outside the domain of empirical science. Some researchers argue that the controversy reflects the natural evolution of scientific understanding as it approaches the ultimate boundaries of physical reality. Just as quantum mechanics force scientists to accept counterintuitive concepts like wave-particle duality and quantum entanglement, multiverse theory may represent the next conceptual revolution required to understand cosmic reality at its deepest level. The mathematical consistency and explanatory power of multiverse models, combined with their natural emergence from well-established theories like quantum mechanics and general relativity, suggest that these concepts may be pointing toward genuine features of reality rather than mere mathematical artifacts. The debate has also sparked new approaches to testing multiverse theories through indirect observational signatures. Researchers are developing increasingly sophisticated techniques for analyzing the cosmic microwave background, searching for statistical patterns that might reveal information about cosmic boundary conditions or interactions with parallel realities. Advanced computer simulations are exploring how different multiverse scenarios would influence the formation and evolution of cosmic structure, providing testable predictions that could eventually distinguish between competing theoretical frameworks. The implications for our understanding of cosmic scale are staggering. If current multiverse theories are correct, then our observable universe, with its nearly 100 billion light-year diameter and trillions of galaxies, represents just one tiny bubble in an infinite cosmic foam. The true scale of reality would encompass not just the spatial dimensions we can observe, but infinite variations in the fundamental laws of physics, the properties of matter and energy, and the very nature of space and time itself. These developments are occurring against the backdrop of ongoing mysteries in observational cosmology, particularly the Hubble tension that has puzzled researchers for several years. Different methods of measuring the universe's expansion rate continue to yield inconsistent results, with local measurements suggesting faster expansion than predicted by observations of the early universe. This discrepancy might indicate that our understanding of cosmic evolution is incomplete, or it could point toward new physics that operates on cosmic scales. Recent theoretical work has proposed various solutions to the Hubble tension, ranging from modifications to general relativity to the existence of new forms of dark energy that evolve over cosmic time. Some researchers have even suggested that the tension might be resolved by recognizing that our local region of space exists in a slightly different cosmic environment than the universe as a whole, potentially providing evidence for large-scale structure that extends beyond our observable horizon. As we stand at this moment in cosmic history, we are witnessing a remarkable convergence of theoretical insight and observational capability that is revolutionizing our understanding of universal scale and structure. Advanced space telescopes are revealing the cosmos at unprecedented scales and distances. Quantum computers are demonstrating phenomena that challenge our basic assumptions about reality, and theoretical physics is developing mathematical frameworks that encompass possibilities far beyond anything our ancestors could have imagined. The questions we face today about cosmic scale and multiverse reality represent some of the deepest challenges in human intellectual history. Whether we live in a single universe or an infinite multiverse, whether quantum mechanics reveals parallel realities or simply reflects the strange nature of our own reality, whether the cosmos extends infinitely beyond our observations or curves back on itself in higher dimensions, these are questions that push the boundaries of human comprehension while simultaneously demonstrating the remarkable power of scientific inquiry to explore the deepest mysteries of existence. What emerges from this cutting-edge research is a picture of reality far more complex, creative, and magnificent than previous generations could have conceived. We find ourselves not just inhabitants of a vast universe, but potentially citizens of an infinite multiverse, where every possibility finds expression, and where the very concepts of scale, existence, and consciousness take on meanings that transcend our everyday experience of reality. Let's move to our last part of the documentary, where we bring together all the threads of our cosmic journey and reflect on what it means to be conscious observers in a universe whose true scale may extend far beyond anything we can directly experience. This final chapter is our moment to step back from the technical details and mathematical frameworks we've explored, and instead contemplate the profound implications of what we've discovered about the nature of reality itself. Throughout this journey, we've traveled from the human scale of our everyday experience to the edges of observable reality and beyond, exploring concepts that challenge the very foundations of existence. We began with our ancestors' simple observations of Earth's curvature, progressed through the recognition of our galaxy as a vast island of stars, discovered billions of other galaxies scattered across an expanding universe, and finally ventured into theoretical realms where our entire observable cosmos may be just one bubble in an infinite multiverse of parallel realities. The progression of these discoveries reveals something remarkable about human consciousness and our capacity for understanding. Each expansion of scale initially seemed to diminish our significance, relocating us from the center of creation to increasingly peripheral positions in larger and larger cosmic structures. Yet paradoxically, each revelation also enhanced our understanding of our own remarkable nature as conscious beings capable of contemplating the very cosmos that created us. We are not separate from the universe we study. We are expressions of its most complex and creative capabilities, arrangements of matter and energy that have evolved the ability to observe, measure, and wonder at the cosmic context of our existence. The current state of cosmological research in 2025 presents us with a fascinating picture of reality that combines solid observational achievements with speculative theoretical possibilities that stretch the boundaries of human comprehension. We can now measure cosmic distances with unprecedented precision, map the large-scale structure of the universe across billions of light years, and observe galaxies as they existed when the universe was only a few 100 million years old. These observations have established that our observable universe extends nearly 47 billion light-years in all directions, contains more than 2 billion stars, trillion galaxies, and has been expanding and cooling for 13.8 billion years since the Big Bang. Yet these remarkable observational achievements have also revealed deep mysteries that challenge our understanding of cosmic reality. The discovery that cosmic expansion is accelerating rather than slowing down implies that 68% of the universe consists of mysterious dark energy whose nature remains completely unknown. Another 27% appears to be dark matter that interacts gravitationally but not electromagnetically, making it invisible to all forms of electromagnetic radiation. The ordinary matter that makes up stars, planets, and living beings represents only about 5% of the cosmic inventory, suggesting that we are literally aliens in our own universe, composed of the minority component in a cosmos dominated by substances we cannot directly observe or fully understand. The ongoing Hubble tension, where different methods of measuring cosmic expansion yield inconsistent results, hints that our understanding of cosmic evolution may still be incomplete. New research from the University of Queensland suggests that the complex gravitational interactions between matter and cosmic voids may account for some of the puzzling features previously attributed to dark energy, potentially revolutionizing our understanding of cosmic dynamics. These developments remind us that cosmology remains a dynamic field where new discoveries continue to reshape our conception of universal structure and evolution. The multiverse theories we've explored represent perhaps the most radical expansion of cosmic scale ever proposed, suggesting that our entire observable universe may be embedded in realities so vast that they transcend ordinary concepts of size and distance. Whether we consider Max Tegmark's mathematical universe hypothesis, the eternal inflation scenarios that predict infinite bubble universes, or the many worlds interpretation of quantum mechanics that suggests reality continuously branches into parallel timelines, we encounter possibilities that challenge the very foundations of existence and identity. Recent developments in quantum computing, particularly Google's Willow chip, have reignited debates about whether quantum phenomena provide evidence for parallel universes. The chip's ability to solve computational problems that would take classical computers longer than the age of the universe to complete has led some researchers to argue that such extraordinary capabilities can only be explained if quantum systems operate across multiple parallel realities simultaneously. While this interpretation remains controversial, it illustrates how practical technological achievements continue to intersect with the deepest questions about the nature of reality. The philosophical implications of these scientific developments extend far beyond academic cosmology into fundamental questions about meaning, purpose, and what it means to be conscious in a potentially infinite cosmos. If multiverse theories are correct, then every possible variation of your life is being lived by some version of yourself in parallel realities. Every decision you could make is being made somewhere in the vast ensemble of possible worlds. And consciousness itself becomes a fundamental feature of reality that manifests in infinite forms across infinite realities. These concepts force us to reconsider traditional notions of uniqueness and significance. In a multiverse where everything that can happen does happen, what makes any particular experience special or meaningful? Yet perhaps this is precisely the wrong question to ask. Rather than diminishing the significance of individual experience, multiverse theory might reveal that consciousness and awareness are so remarkable that reality requires infinite variations to explore their full potential. Your capacity to wonder, to love, to seek understanding, and to experience beauty may be so valuable that the cosmos creates countless versions of these phenomena across all possible realities. The search for meaning in an infinite multiverse ultimately leads us back to the immediate reality of our own experience. Whether you are unique in a single universe or one among infinite copies in parallel realities, your consciousness represents something extraordinary. Matter organized to the point where it can contemplate its own existence and feel wonder at the cosmic context of its being. The atoms in your body have journeyed through space for billions of years, cycling through stellar cores and interstellar clouds before becoming organized into the complex chemistry that gives rise to thought, emotion, and awareness. From this perspective, the ultimate scale of the universe becomes not a source of cosmic insignificance, but a revelation of cosmic creativity. Whether reality encompasses a single expanding universe or infinite parallel worlds, whether consciousness arises once or countless times, the mere fact that existence has organized itself in such a way that conscious beings can emerge and contemplate these questions represents something magnificent and precious. We are not accidents in an indifferent cosmos, but expressions of the universe's most remarkable achievement, the emergence of awareness, understanding, and wonder. As we reach the end of our journey through cosmic scale, we find ourselves confronting questions that may ultimately transcend the boundaries of scientific inquiry. Science has carried us from measurements of Earth's circumference to concepts of infinite parallel realities, revealing a cosmos far stranger and more magnificent than our ancestors could have imagined. Yet the deepest questions about why anything exists at all, why the universe has organized itself to support consciousness, and what lies beyond the boundaries of all possible observation may require forms of understanding that transcend purely scientific approaches. What remains clear is that our exploration of cosmic scale has revealed consciousness to be one of the most remarkable phenomena in known reality. The fact that the universe has evolved arrangements of matter capable of contemplating the cosmic context of their own existence suggests that awareness and understanding may be fundamental features of reality rather than accidental byproducts of complexity. In contemplating the scale of the cosmos, we discover that we are not separate from the universe, but are ways the universe has developed to observe and understand itself. Tonight, as you rest and prepare for sleep, remember that you are part of this magnificent cosmic story. Whether you exist in a single universe containing trillions of galaxies, or in one bubble among infinite parallel realities, your consciousness represents something precious and remarkable. You carry within yourself atoms forged in stellar cores billions of years ago, organized into patterns complex enough to experience wonder, love, and understanding. Your ability to contemplate the vastness of cosmic scale, to feel awe at the beauty of existence, and to recognize your connection to the larger cosmos represents one of the universe's greatest achievements. The question of how big the universe is may ultimately be unanswerable, not because of limitations in our instruments or theories, but because reality itself may be fundamentally unlimited. We stand at the shore of an infinite ocean of possibility, having learned to measure waves and currents while recognizing that the vast depths extend beyond every horizon we can conceive. Our journey of cosmic discovery has only just begun, and future generations will undoubtedly reveal wonders that make our current understanding seem as primitive as ancient maps that showed the Earth as a flat disk surrounded by dragons. In the quiet moments before sleep, take comfort in knowing that you are part of something infinitely larger than yourself, while simultaneously representing one of its most complex and beautiful expressions. The universe has revealed its secrets slowly and patiently, rewarding human curiosity with insights that expand our conception of reality itself. Your consciousness is both a product of cosmic evolution and a participant in the ongoing process by which the universe comes to understand its own nature, scale, and magnificent complexity. Sweet dreams, cosmic voyager. The universe continues its expansion through the night, patient and eternal, magnificent beyond words. And you are part of its most beautiful chapter, the part where it awakens to its own wonder and recognizes the infinite creativity that brought you and everything you can observe or imagine into existence.